Now, after seeing how we can balance and unbalance the assignment problem, now let's see how we can solve the assignment problem. We are going to use the Hungarian method to see how we can solve assignment problems. So the first example is concerned about the balanced minimization assignment problem. So the question is, assign the 5 jobs, J1 up to J5, to 5 machines, M1 up to M5, so as to minimize the total cost. Okay, so we have this table representing the machines and the jobs, and inside here, these are associated costs of assigning these different machines to different tasks. Okay, now let's see the solutions. The first step in Hungarian methods, first you need to check whether the given assignment problem is balanced or not. Okay, if it is not balanced, you need to balance and then you go to the other steps. So step number 1 is checking whether the given assignment problem is balanced or not. So basically, as you have seen in the question, is that we have 5 jobs and 5 machines. That means the assignment problem is balanced. Now, after checking for the first step, the second step is called the row reduction. In row reduction, basically, I just picked this matrix from this table. Okay, so I just picked this cost matrix inside, leaving out the labels. And now, the row reduction requires that you identify the minimum cost, okay, from each row, okay, and then you subtract that minimum cost throughout the entire row. So from the first row, we have identified the minimum coefficient as 3, and from this row, the minimum coefficient is 1, and this row, the minimum coefficient is 7, and from this row, the minimum coefficient is 12, and the last row, the minimum coefficient is 5. Now, as I said, in row reduction, we are going to take these coefficients and then we subtract throughout the row, okay? So 3 is going to be subtracted throughout this row, 1 throughout this row, 7 throughout this row, and up to 5, okay? So if you do that, you will end up with this matrix here. This is the reduced matrix by subtracting respective smallest element in the rows, okay? Now, after row reduction, what next? We have to reduce again the matrix using the column reduction, okay? So in column reduction, we do the same, but the column reduction follows after row reduction. So this matrix here is a result of row reduction. So from here, we perform the column reduction. So we identify the smallest elements from each column, okay? And then these elements we subtract throughout this column and we will end up with this matrix here. So after having this matrix, performing row and column reduction, and having this column reduction matrix, the last one here, okay? Now we test for optimality of this matrix, whether we can make an assignment from this matrix or we need to improve this matrix so that we can have an assignment which will give us the minimum cost of allocating the machines to those jobs. Okay, now let's pick this matrix, the column reduction matrix. So this one, and test for optimality. If this matrix will give the optimal results for allocation of the machines to jobs. And the optimality here, we are looking whether this one will give us a minimum assignment cost. So how are we going to test for optimality? We test by drawing a minimum number of lines to cover up these zeros we see in our matrix. Okay? So how can we attain a minimum number of lines covering all zeros in our matrix? First, you need to identify a row or a column with the largest number of zeros. For instance, here, you can see this row here have 3 zeros, while this one have 1 0, 1 0, 1 0, 1 0. If you go column-wise, you can see we have this column have 2 0, this one have 2 0, this one have 1 0. So this row have a maximum number of 0. So we need to cross this 0 first. If we cover this 0 with a line, then we go again and check which row or column have a maximum number of zeros. We have this column here. This column have a maximum number of 0, which is 2 0 in this column, while the others, column or row, have 1 0. So we cover up this column. Then the remained have just 1 or single 0. So you draw a line to cover it, either vertically or horizontally. There is no problem about that. So you just cross those rows, and we have managed to cover all zeros in the matrix. Now, what next after covering all zeros in our matrix? So the optimality of an assignment problem is attained when the number of lines which cover these zeros are equal to the order of the matrix, okay, or size of the matrix. So here we have how many lines? We have 1, 2, 3, 4, while the matrix is 5 by 5. That means the number of lines are not equal to the number or order of the matrix, and therefore we cannot say this is the optimal solution. So we need to improve this solution. So we say that the number of lines drawn to cover up the zeros are not equal to the order of the matrix, and then the optimality is not reached. We are going to improve this solution. How are we going to improve the solution? Go around this matrix, look for the least element, the smallest element, which is not covered by the line. The least element which is not crossed or covered by a line from these remained elements is 2. So we are going to take this 2 and subtract to each element which is not covered by a line, and adding these intersection elements, this one, that is 6, 3, and 2, and leaving other elements which are just crossed once as they are. So in doing so, we are going to end up with this matrix. So after improving the solution, now we have to test again for optimality. So as usual, look for a column or a row with a maximum number of 0. We see that we have this row again with 3 zeros, and we are going to take from there, cross that row, and we have this row with 2 0 and this column with 2 0. We can choose either one to cross column wise or row wise. So if we go row wise, we are going to cross this row, and then we remain with these 3 rows with single zeros. So we can cross in either way, row wise or column wise, because each row or column contains a single 0. So crossing or covering the remaining 0, we are going to end up with this number of lines where we are going to have 1, 2, 3, 4, 5 lines. And the order of this matrix is 5 by 5. Therefore, since the number of the lines equal to the order of the matrix, then we attained our optimality of our solution. Okay, after attaining optimality, or after testing for optimality, and we see that this is the optimal solution for an assignment problem, now we are going to make an assignment from this matrix, because this matrix is the optimal one. So picking this matrix, we are going to start to make an assignment. So how are we going to make assignment? Basically, in assigning a certain machine to perform a certain task, we are going to assign a machine to a specific task where there is a 0 cost. Okay? And that 0 should be single, either in a column or row. For instance, this row have 2 zeros, so we cannot make an assignment in this row because there are 2 zeros. In this second row, we have single 0. We will make an assignment here. So we just cross-check for all rows, and then we start to make an assignment. So starting from top, we see the first row have 2 zeros. We cannot make assignment there. We are going to start with the second row and make assignment by drawing a square around this 0. So we are going to make assignment here. And when you make assignment here, okay, remember we assign one machine to perform one job. So we don't expect this job, because in this column, which we have made our assignment, it cannot be assigned to any machine, because the principle of assignment, one resource to perform one activity. So wherever there is any 0 in this column, we are going to cross it. And whenever there is any 0 in this row, we are going to cross it, because one machine, one task. The machine also is not going to be assigned another job. So single machine, single job. So in this column, we see that there is a 0 here, and we are not going to assign another task in this column, because this job have already assigned to machine 2. So we are going to cross this 0, crossing this one. Okay, after crossing this one, now we go again back, checking for a row or a column which we didn't assign, but having a single 0 or a single unassigned 0. So coming in this row, the fourth row, you can see that we have single unassigned 0. So we are going to make an assignment there. And then we check in this row whether there is another 0, because we need to cross it, or in this respective column. Okay, we can see that at the top there is unassigned 0, and we are going to cross it because this job have been already assigned a particular machine to perform this job. After that, we go back again. We see that the first row have one or single unassigned 0. Okay, so we make an assignment there, and then in this row we are not going to assign any other task for this machine. In this column, we are going also to cross any 0, because we are not going to assign any machine to perform this task, because it have been assigned to machine 1. So we are going to cross the 0 below. Okay, and then we check again. First row we have already assigned. Second row we have already made an assignment. Third row we didn't make an assignment, and we have a single unassigned 0, and we can make an assignment there. And we check if there is an assigned 0 in this column or row, so that we can cancel it. And we can see that in this column we have no unassigned 0, with the same for the row, we have no unassigned 0. So this task have been assigned to machine 3. And lastly, we have the last row with single unassigned 0. We make an assignment there. We check for the column whether there is an assigned 0, so that we can cancel it. There is no unassigned 0. And the same for the row. There is no unassigned 0. So the matrix here represents the assignment, which basically will give us the minimum operational cost. Okay, after making these assignments, then we can summarize our results, and we have this summary. This is the mapping of the assignment to the original matrix, M1 to J1, M2 to J4, and to M5 to J2. So we summarize the results of assignments for in this table. So this is the table which basically you need to prepare for your summarization. So we have the machine, we have the job, and these machines assigned to respective tasks, which gives us the minimum operational cost. Okay, so this is about solving a balanced minimization assignment problem. So how can we solve for unbalanced at the same time it is for maximization? Now let's look on this example where a manager has 5 subordinates and 4 tasks. The subordinates differ in efficiency. His estimate of the production each would do is given in the table. So the question is how the task should be allocated 1 to 1 man so that total production is maximized. So this matrix basically gives the efficiency index. Okay, this counts for the efficiency of each subordinate. So we have 5 subordinates, 4 tasks. The problem is not balanced. But before balancing the problem, we have to transform, because the problem is maximization. Now we are going to transform a problem from maximization to minimization. And how are we going to do that? Let's see on the next slide. So transformation basically is performed by subtracting all elements in the given matrix from the highest element. Okay? And we ignore the minus sign, where in this table you can see the highest element is 11. So we are going to subtract 11 throughout all elements in this matrix. So by doing so, we are going to end up with this matrix, which is a transformed matrix after subtracting 11 to all elements in this matrix. So after transforming the matrix or the problem now into minimization problem, we need to balance the problem. So how are we going to balance the problem? After transforming, we need to balance the transformed assignment problem. So how are we going to do that? To balance, we are going to add a dummy task after the 4th task to balance this matrix, because we have 5 subordinates, 4 tasks. So we need to balance by adding a dummy task which is going to have the 0 coefficients. So we are going to add that dummy task, and this is the matrix which have been added a dummy task. So you can see we have the row 5 with the dummy entries of zeros, and now this assignment problem is balanced. After balancing the assignment problem, now we can go for row reduction. We picked the elements in the matrix, and from each row we identify the smallest elements, and you can see we have identified the smallest elements, and we subtract this smallest element from the respective row where they come from, and we end up with this matrix. So this matrix also will undergo column reduction, but in this column, in each column you can see 0 is present. We have 0, 0, 0, 0, 0 here. So the least element in each column, 0 is there. So the column reduction basically will look like this one. So this is the column reduction, and as I said, it is similar to the row reduction because each column have a lowest element which is 0, so there will be no changes. So this is the column reduction. Now from this column reduction, we have to perform optimality test to see whether this matrix here will give us an optimal solution which we need. Okay. So let's perform the optimality test. As usual, we are going to cover the zeros in this matrix, but we are going to start covering row or column with the maximum number of zeros. So the last row have all elements 0. We are going to cancel that or to cover those 0, followed by this column have 2 0. We're going to close that, and the other column is this one, have 2 0. So you can see we have covered all zeros with the minimum number of lines. Okay, how many lines do we have? We have 3 number of lines covered the all zeros in this matrix, but the order of this matrix is 5 by 5. So the number of lines are not equal to the order of the matrix, and therefore the optimality is not reached or attained, and therefore we need to improve our solution. And how are we going to improve the solution? Look on these elements which are not covered by lines, and then pick the lowest element or least element. The least element here is 2. We are going to subtract all elements which are not covered by 2, and adding 2 to the intersection elements of the lines. That means here we are going to add and here we are going to add, but the other elements which are crossed just once by a line, we are going to leave them as they are. So we are going to do that, and this will be the outcome of that improvement. Then after this improvement, we need also to perform again the optimality test. So we cross or we cover zeros with the minimum number of lines. So as usual, look for a row or column with the greatest number of zeros. So you can see the last row have 3 0. If you go column wise, you can see some columns have 2 0. So we are going to cover the last row, then followed by a line, this one, a column with 2 0. We remain with the 2 row or column, okay, with zeros, and we have this column here having 2 0. We are going to cover it, and we remain with this column or row with single 0. We are going to cover it. So we are going to end up with how many lines? 1, 2, 3, 4. Still, this is not optimal solution since the number of lines drawn are not equal to the order of the matrix. Then still the optimal solution is not yet. So improve again the solution. To improve that, we take this smallest element, which is 1 here. We subtract to these uncovered elements, and we will add to these intersection elements, and we are going to leave the elements which are just crossed ones as they are, and therefore we are going to end up with this matrix. So after having this matrix improved one, also we are going to cover the zeros with the minimum number of lines. As usual, look for a row or column with the maximum or greatest number of zeros. So we have this column with 3 zeros. This row have 4 zeros. We are going to cross the row with 4 zeros. Then we go through column or row with the greatest number of 0. We have rows or columns with 2 zeros. Then we are going to cross the next row. Okay, so crossing that one with 2 zeros. Then we cross that one, and the last one is that. So here we end up with the optimal solution because the number of lines are equal to the number of or order of the matrix. So the optimality is reached, and we are going to make an assignment from this matrix, and the assignment will be to the row or column with single unassigned 0. So we have first row with single unassigned 0. We make assignment there, and we cross all other zeros below or in a respective row. So since we have assigned here, we are going to cancel or to cross this other 0 because single job, single machine. Then we check for another row with an assigned 0. We have this one. We make assignment here, and we are going to cross the 0 above it and below it. Okay, so that no other task is going to be assigned to this subordinate. Okay, so after that we go through again. You can see we have this fourth row with single unassigned 0. We assign there, and we cross the 0 above it so that no other subordinates will be assigned this task. So going downward there, you can see the last row have a single unassigned 0. We make assignment there. We cross the 0 in this column, and the last one will be the second row with single unassigned 0. We make assignment there, and then we have the optimal assignment from this problem. Now we can now summarize by comparing to the original matrix before transformation, and you can see that we have how many tasks? We have 1, 2, 3, 4 tasks. And we have how many subordinates? 1, 2, 3, 4, 5 subordinates. We eliminate the dummy task because it have no significance since its coefficients or its efficiency is 0. So we are going to map this one into this matrix, and here we have the summary mapping. We have task 1 to subordinate C, task 2 to subordinate D, task 3 to subordinate B, and task 4 to subordinate A. So this is the summary of the assignment, and this gives us a total of maximum efficiency which is equal to 34. So this is how you can solve the assignment problem, which is unbalanced, also a maximization problem using the Hungarian method. Okay, thank you for watching. Don't forget to subscribe, like, comment, and share this content. Goodbye.